All right, so in the last class, we were looking at gold mine problem, and the problem was a thief is standing at the beginning of a gold mine, and he wants to go through the gold mine and try to find the best possible path which gives him maximum gold. So we went through all this, we tried paraphrasing, we tried creating the function signature. We even wrote a helper code to help us get into some other rows. We wrote this, and for each of the children, we tried finding how to get to the children. And the homework was add data structure, because once you add data structure, it becomes memoization. And once we do iteration, it becomes DP. Now, then we opened, and you had sent me this link, path with maximum gold, right? So path with maximum gold, and you had a solution for it. But I realized what happened was, can you still hear me though? Can, who am I talking to?
Yes, it's perfect.
Okay. So what I realized is, this particular problem was not a dynamic programming problem, because that had something known as backtracking, which we haven't reached yet, right? So that is the first mistake you made. You thought this was a DP. This is a DP problem. I'm not denying that, but it has slightly more added stuff. So what I want to do today is show you the other problem, which is this problem that we are looking at, the gold mine problem, right? And then, so this is the actual gold mine problem we were discussing last day. So it says, given a gold mine of n star m dimensions, each field in the mine contains a positive integer. And in their case, you can only move right up, and right down. I think our case, we had, I forgot, left, top, bottom, but doesn't matter. Based on the question, it'll change. And find out the maximum gold. For example, if this is the matrix, person goes in, and the maximum gold is 2, where you start from 1, 0, which is 2, 2, 2, 1, which is 6, plus 4, 1, 2, 1, 2, 4. So this is 2 plus 6 plus 4, 12. Okay, perfect. So what I want to try doing today is, we are going to write this code up first, because we already did that. And we might as well slowly build from that. And then if we have time, I will slowly introduce backtracking. But this is actually very interesting, that the whole backtracking problem. It's a very simple, okay, I'll tell you what the backtracking part here is. This one, like, never visit a cell with 0 gold, and you cannot visit the same cell more than once. So the major difference, okay, let me write this down in the, okay. So this is DP lecture, April 17th, 2024. Right, so I know we haven't introduced backtracking, but there is a set of problems known as backtracking. And then we have DP, dynamic programming. So dynamic programming is, at the end of the day, an optimization problem, which means give me, the example is, give me max gold, right? It's optimization problem, which is why we usually have like max of left child, right child, etc. Backtracking is nothing but, it's a purely find path kind of problem, and we will see that soon. And this is, for example, if you're a rat, you're stuck in a stuck in a maze like this, and this is where you're starting. And let's say there are only a couple of ways you can get out. So I'm going to say just randomly draw this. So you can probably go here, here, here. Some other ways are blocked out, but this is the only way out. So the goal there is to find a path, right? Go through some of the mistakes, like maybe it goes here, finds there is no path. So you go back and backtracks and tries another path. So that is a different problem. The answer to this is usually yes, there's a path, or no, there is a path, or print the path, right? There is no optimization there. So that is the little flavor they added onto that question, which is why it became very complicated and confusing. So let's see if we can just plain tackle the real problem itself, the dynamic programming problem we were looking at. So to remind you, the problem was we have a gold mine, and someone is trying to come in here, and we want the person has to come out with the max gold. So whenever this kind of confusion happened, the first thing I did was go back to basics, right? So I thought of Fibonacci, go back to the basics and try to find what did we do in that case. So let's call it index 0, 1, 2, 3. Tell me when the screen, I accidentally go below, okay? I'm writing on my parents 4, 5.
Okay.
Okay, so Fibonacci 0, 0 is 1, first value is 1, second value is 1, third value is 2, fourth value is 2 plus 1, 3, and 3 plus 2, 5. Okay, so this is the very first thing which we started where we said, okay, let's write this recursively, right? And then we'll add a memoization, and then we'll write it iteratively, and we'll call it TP. Now, Fibonacci, if you think about it, it is the recursion problem itself, right? Recursion alone is a top-down approach. So this is bottom, this is down, whatever you want to call it, and this is top. So what we are doing is when you're asked, like, give me fib of 5, we start with 5, we ask or fib of 5 is usually this index. We start with 5, we ask 3 and 4, and 3 and 4 in turn ask 2 and 1, etc., etc. So we keep going back until we hit an exit case, which is 0 or 1, and then all this starts returning back up, right? So, and if you remember, the one question whenever we were writing recursion, the first step was function signature. And what was the second step?
Me, myself,
Yeah, me,
parting
myself,
gift,
my children. And then we also write the exit condition before
exit
writing the
condition.
parting gift, okay? So,
Okay.
so far, all the problems we saw in dynamic programming were linear. We were thinking, hey, here is me standing there.
Can you scroll down?
No, I'm sitting inside Fibonacci only there. Fibonacci that.
Okay.
So here, like I'm this guy here, right? So this guy, that's me. I'm sitting there. On one side, there is my children. On the other side, there is a parent. And my goal is, someone tells me like, hey, all my children work is done. I do my job and I give it to my parent. I return it to my parent. So this, like basically we are taking the children's value, something, do something to it. So let's call it CH value. And I'm doing something to it and returning it to my parent. So that concept is very important because what we are doing here is exactly the same, but in 2 dimensions. Right, so here we have the grid. Let's say this is the actual Goldmine grid. And what is happening is, this is where we start, like the person is walking in. This is your bottom. Again, scroll down, sorry. This is the bottom, this is the down, whatever. This is the top, this is where parent is. This is the child, right? So this, everything is going in this direction because what the actual question we are asking is, when we get out of here, what is the best way to get out? So the best way to get out is we ask this cell, the cell asks some other cell, maybe ask this cell, then it keeps going backwards and stops at when we hit this guy, and then we build it back up, okay? So what I'm trying to say is that is exactly the code we wrote earlier, which is here, we are saying me as the miner, I'm getting answers from C1, child 1, child 2, child 3, and I'm getting the maximum value of all this and returning that, adding my value to it and returning that to my parent, right? And this is, of course, like we discussed in that particular case, it's order of 3 power mn. In this case, exactly same thing, like maybe the only difference is we can only go right up, right down. So what I want to do is just write the code for this again. So let's go to this. And we'll actually try to run it today. So ¿dónde estás mi friend? Okay. So where'd that go? All right, Goldmine problem. And same problem, but let's keep it side by side and see how we can try writing the code for it. So in the screen, perfect. Okay, so here, gold mine of n cross m dimensions. So I'm going to draw the gold mine, which you should be able to see in your screen. All right, perfect. So n cross m, which is usually m rows and n columns, I think. Okay, so our goal is you can start in the top left, or actually you can start in any of the columns. Like you have to be in the first column, you can start in any of the rows, right? Remember we did that helper function, and then we expand and find the best value. So for which we did our def helper function, which is the one which was helping us with the row thingy, which instead of copy pasting, might as well just write. So which is for I in range of I is my rows, range of m, right? I'm gonna call my minor of I comma j. So this is I comma 0 because very first time it goes out, we want to get the first column. We call it local max. We have a global max 0 if local max is greater than global max. We call global max equals local max. Okay, so this was a very simple helper function, and then we wrote our the actual minor function,
I
which if
have one doubt here itself. Like the helper function, why do we have one for loop, and that for loop is basically iterating over that current row or ith row? Sorry, zero is column. Okay, what is this helper method doing?
yeah, the helper method is trying to help us decide where do we start in the first column.
Okay,
Like we know we can start at the first column, but do we want to start at 0? Do you want to start at 1? Do you want to start at 2? Or which one is the best choice, right? So all
so it
I'm
has to be
saying,
first row. We can start from first row or first column.
first, they say here, initially, the minor is in the first column, but can be in any row.
Understood. Okay.
Okay, so in our case, we have 3 choices, which is he can start at 0, start at 1, start at 2, but we have no idea no way to say this is the best start. So we are
Mm-hmm.
letting the code do that for us, which is we are hard coding 0, which is basically the column value, the very first column value, and I is your row value, which changes between 0, 1, and 2. And all we are doing, finding the local max and finding the biggest one out of it, right? And we return global max on that. So
Understood. Yes. Thank you.
yeah, this I'm not gonna make it interactive because we already did this. I'm gonna quickly write this through. And so minor was I comma j, and we are probably passing what do we want, the maze, right? The grid. So okay, let's create a grid also and pass it. So we have to pass grid. We also have to pass m comma n. So a couple of to-dos is create grid, calculate m and n, and we have to pass that in the calling function, which is pass the grid, comma m comma n. Okay, so And here, the only thing we did when we were writing the function was if somebody tells me this is the best path so far, this you're here. Oh, sorry. Scroll up, scroll up, scroll up, scroll up, scroll up. I lost the cursor. Okay, so this is the one in this case where you're only allowed, now going back to the grid, right? So let's think this through. You're a person standing here, and your choice is you can either go right or top left, or you can go this way. So that is your bottom-up thought process. But when you look at it top-down, what you're essentially saying is that you have, oh, sorry, maybe the children thing, we wrote it wrong here, right? Sorry, we have a bunch of children and we are saying, so the child is here and this is the parent here. So we as the person standing in this particular cell has options from 3 of these children. Our job is to pick the best of these 3 and add our value to it, right? So that is exactly what we were trying to do when we went writing each of these minor thingies, which was, what was that? Okay, so we wrote the function signature, which was the first step, and our goal was find the max of my children plus add me and return me, right? Okay, that's it. That's all we write right now. Then we go look for the exit condition. The exit condition we were saying was if we are crossing the grid, right? If, let's say, going out of the grid, I less than 0 or j less than 0 or I greater than or equal to m, which is the length of the number of rows, j greater than or equal to n. In all these cases, this is our base exit condition, we return 0, okay? So now the only thing left is we need to expand this line here, which we call parting gift. So this particular question, they say we can only go right, top, left diagonal, and top diagonal and bottom diagonal. So what I'm going to do is my children, I'm going to call it right child, top diagonal child, bottom, again, scroll down. Bottom diagonal child is, so plus, so max of RCH, top diagonal CH, PDCH, and we haven't even defined that yet, plus me. Me is grid of I, comma, j. Okay, so, and here is the parting gift, which we keep insisting, do not think it through. All your job is add minor, right? Minor, 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 same function, add the repeating parts, grid, m, n. So never open up a recursion and think it through, it will destroy you. But if you can get control over it, just like emotions are amazing if you can have good control over it. So now let's say, what is the meaning of going right? Going right is what stays static? Like, does the row remain static or the column remain static?
In the first top right, right?
Yeah, so let's talk it like this is the right child, right? This thing I'm writing on top here.
So row remains static, column increases by 1.
Right. So in this case, the row remains static and the column increases. So we have I static. Can I say this one is j plus 1, the column increases. How about this guy? We call it TDCH. Top
I minus 1 and j plus 1.
I minus 1, j plus 1. And how about the bottom one?
I plus 1, j plus 1.
That's it. That's their question. That's all they're asking, right? So see, we already are done with the complicated code for dynamic programming. So my point was, let's try writing this up ourselves. Like I said, we will eventually get to the same problem you are working on, because that is important, but even just before to do that, let me create a new project here, online GDB Python 3. So temp gold miner, probably even have a name called Activia here, V2. Oh, by the way, are you added to the, were you there in the call for Chatur?
No.
Okay, never mind. Okay, so what we're doing here is we need to first create the grid. So let's go shamelessly copy the grid from their code. We are not going to look at anything else. Just gonna call it grid. Okay. Right. And let's call it grid because that is the term we use. So let's call it grid. We want M, which is the length with a number of rows, which is length of grid. N equals length of grid of 0, which is the number of columns. So then we have a def helper, which really doesn't do anything. Its job is, oh, grid and M are global, so you probably don't even need to pass it. But helper's main job is for I in range of M, we create global max equals 0. Local max equals minor of I comma 0. And if local max greater than global max, we replace global max equals local max, right? And all this function does is return global max. And our driving code will be print helper, like whatever we return, which should print 12 in this case. So then we are doing def minor. Okay, so like I said, we were passing I comma j, but right now we don't have to pass grid. It's probably available in our thingy, our global variable here. So we wrote the function signature, my max of all 3 children plus me, that's what I'm returning. So me is grid of I comma j. So I'm, like I said, we already wrote this, which is why I'm rushing through and not letting you complete the code. So
Understood, yes.
now is, we want the exit condition. When do we exit? When I is less than 0 or j is less than 0, we are falling off the grid, or j greater than or equal to n, which is the number of rows, or I less greater than or equal to m, which is the number of columns. Okay. So whenever any of these happens, we're just gonna say return 0. That's our return point. And all we need to do is create children. So our right child is same thing, minor something. We are not gonna touch it. PCH, my top diagonal child is something minor. Bottom diagonal is minor of something else. We haven't decided. All we are doing is max of RCH, comma TCH, comma BCH, right? And this is the one we decided, where we'll go I comma j plus 1 for right, and I minus 1 comma j plus 1, and I plus 1 comma j plus 1. And let's do our standard stuff, which is, we did all this where, just remember, where are we? Okay, this one. So we were, okay, we did paraphrasing, core logic. That is what happened here. Core logic, we did all the recursion stuff. So the other things we are left with is edge or null cases, or more importantly, we want to do a try run, which will help us with edge or null cases. We even did an online coding already and read out loud. So let's do a try run here itself while we have it here. So let me draw exactly their grid in this, our sheet here. Where is this? Okay, perfect. Here, I am going to draw the grid Geeks for Geeks gave us. Don't they? Okay, here. And this is how the grid looks like. Wait, what did we do? 1315, 13152241. Okay. 13152241 50230612. Okay. 1315.
Can you please change the color? It's very light.
Light, please go. Let's just go this one maybe. 1315, is that better?
Yes.
Okay. 1315, that's our grid. 2241. Very helpful. 5023. And we are adding 0612. Okay, so our goal is we as a person standing outside, we don't know which one of these four options is best for us. So we're going to start with, let's call it M. This is N 0123, 0123. We're going to start with 00, which is going back to our code. Move with them. All right, going to go to the helper code first. We are going to give it 00 comes in here. So this is 0, this is 0. We go back to the minor code, and the minor code, this comes in 0, this comes in 0. Is it less than 0? No. Okay, so none of this happens, which is none of these conditions. You're not returning anything there. So now max of my children. So this is right child is I is remains same. J becomes 1. The left child of the first guy is of course -1. And then, excuse me, J plus 1 is 1, J plus 1 is 1, this is +1. Okay, so let's go back in with the right child go back here, 0, J is 1. Okay, comes back here, is I less than 0? No. Is J greater than or equal to M? So remember, M is, in this case, is 4 cross 4. No, so we come back to, so we are here. This is our right child, and we are asking the right child, what is the value? So it's not exit yet. So we go to its right child. All right, this is going to take a bit of time, but let's also look at this guy, TD, the diagonal child. So there is no diagonal child in the first case. So when we go in with -1, 1, that will give us this check, which is I less than 0. So that will return. So that will be 0 returning. This will be 3, and the bottom diagonal is also going to return, and it's going to keep chaining from there. So far looks good. All we have to do is we are max. Okay, let's read it out. Where is the next step? The next step was paraphrase is done, core logic is done, try run is done. Edge or null cases. What else can this be? The grid is null, and okay, let's come back to that, right? Grid is null and all that stuff. Let's at least see if the basic code works, online code, what we wrote. Okay, let's look grid 1, 2, 3, 5, length of grid of 0, and then what the fuck, how the fuck did we get inside? What a stupid idiot. What the fuck? All right. My dog is right here, and this Amazon guy came here, and she hates Amazon people. If the damn door was open, I would have had a my hand. Yeah, no, you're beautiful. You're beautiful. Yeah, maybe. Okay, so let's go. Helper global max is 0. I in range of M, local max minor of I comma 0. If local max greater than global max, return global max minor of I comma J. If I less than 0 or J less than 0 or I greater than or equal to M or J greater than or equal to 10, return 0. RCH is minor of I comma J plus 1, I minus 1, J plus 1, I plus 1, J plus 1. Now all we are doing is returning max of it, and we are printing. Ta-da! Please, please, please. Very funny. Very funny. Okay, so what are we returning? Global max. No, Calista, wait, let's just print global max here. No, wait. What is going on? What am I?
You're not calling the not calling the minor. Oh, so you are calling. Okay.
Never mind. Got it. I wasn't calling the function. I was calling Okay, so we ended up getting 16. That's, let's see, what's the right answer? We are supposed to get,
Yes, it's in the bottom.
okay, wait, we use a different grade. Very smart.
No,
What
no,
grade
no, it's
is this? Okay.
yeah,
16. Oh,
16.
perfect. Okay, we got perfect 16. Okay, great. Right. So this is done.
Nice.
This is the point where we left last day, and we were saying let's move it to the next level, which is let's add a cache to it, right? So now cache gets very interesting. So again, cache is something which I want to re-emphasize here, the same diagram as earlier. So remember, we had a grid. This was the grid given to us. And then we are trying to create a cache next to it. And the grid is, we agreed, this is where is bottom is. And this, wait, maybe it was like we started asking this guy top and this was bottom and our child was here. And then we asked, like, I am in the middle. What do I say? This is my parent. I'm returning to the parent, right? So same idea. Cache is almost always going to be a copy of your actual grid. But the only difference is here on, we are populating things. Like here, the very first, let's see, what was the number? I'm just going to make this up as we go. 5, 1, 3, and 2, 1, 4, 2, 1, 1, 4, 2, 1. Okay, so this guy here, as far as this cell concerns, 2 is the best value, 3 is the best value, 1 is the best value, 5 is the best value. So, but as far as this guy concerned, it is 3 and 2. The best value is 3 plus its own value 1. Sorry, that was 1. And that's all we are looking for here, right? We are trying to build something which is, this guy has 1 plus 1, and my best value is 3, my neighbor's best value, right? So here, the cell above this is my value in the cell 2 plus, which is my best value, 3. So on and so forth. So we are building this up so that next time the same question is asked, we have something in the cache already. So as usual, I don't want to walk into the trap of coding online directly. That screws me up. So let's try adding a cache here and hopefully make it look cleaner. Okay, so the only difference will be in trying to delete all the other colors. Tuck, 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 tuck. Tuck. I don't want to recopy the whole thing. Okay, so what I'm going to do here is in the helper function, we will create a cache. So if I give you m and n, do you know how to quickly create a two-dimensional matrix? Like I want an empty matrix full of zeros, right? Of the same size as my grid. Do you know how to do that? Do you know it, or shall I say? Oh yeah.
Oh, I was talking on mute. So yeah, you can write in the inner list. Yeah, what you wrote was correct. Yeah. So now in the inner list, 0 for
Okay.
no. 0 continue in the inner loop itself initially. Yeah, 0 for just put an underscore. Basically, yeah, in range m. What is the row m? Then close the list, and then for again underscore in range, and yeah.
Okay. So we're gonna say m is 4, n is 4, and do the same thing again. All right, what does cache look like? Okay, perfect. So there's a very interesting thing I want to mention there is, let's say my grid is m is, I have 3 rows and I have 4 columns, right? So your cache is doing good, right? We have,
You want 3 rows? Okay.
yeah, okay.
Yeah.
So that's good. Okay, you see my point, right? But I even discovered something easier to do. Apparently, is one way to do this is just put a 0 in the beginning, star n, star m. And apparently that gives you the right answer. We have 4
Oh,
columns,
okay.
3 rows. So this is something I discovered yesterday, and I thought it might be
Oh,
helpful.
nice. Yeah, I didn't know about that. And in the for loop, yeah, I think we just swapped M and N.
Yeah, that's okay. I mean, our exact mistake doesn't matter. All I'm saying is we don't need to write the whole 4 in range of kind of thing.
Oh, nice. Yeah, that syntax looks cool.
Yeah.
I didn't
So
know.
just remember n is inside, which is the number of columns, and m is outside, which is the number of rows. Because it's
Okay,
like we're
okay.
building columns and then we are building the row.
Right, right, right.
Okay, so here, what we are doing is, all I want to add is, let's say, add a cache here. So I'm going to say, even like a global cache is equal to 0 star m. I already forgot 0 star n star m, and that's my cache. So the cache is there. So what do we have to add in the minor when we come in here?
Can you scroll down?
Oops, shit, sorry, def minor. So how do we add a cache to these guys?
So before returning the res no. Yeah, so before returning the result for grid ij, we will basically store that result in a variable and update our cache ij position with that value. So cache ij is equal to max of all the children plus grid ij, and we will return that value. Also store it.
Okay, so you're saying in this case here, it will be cache of I comma j is equal to this value, or
Yeah,
whatever,
that's it.
return that value, right? Cache of I comma j, or whatever we want to call it. But what if, is this enough?
No, we need to check before doing all of this. We need to check if the cache ij is not equal to 0. If it is not equal to, I think we should, so basically if it's not equal to 0, then we can just return it from cache ij. We don't need to calculate recursion.
Return cache ij, and else we do all this, right? Do everything.
Yes.
Perfect. Okay, let's go back and do our thing quickly on the cache thing, which is 0 star n star m. Okay, so that we don't know what n and m is. Sorry, let's do it here. We call a cache. We define this guy, and only. So you see how easy this is becoming, right? We are so experts in this that we are
Right.
already like just typing it in immediately. If cache of I comma
Yes.
j greater than 0, or let's say not equal to 0. So when you build up DP like this way, it's such an amazingly beautiful thing, and we can quickly remember, we can always go back to our basics and check. Like I've been literally going back to Fibonacci every time I'm in doubt. Okay, and then our out is equal to max, and we do cache. Okay, I comma j is equal to out, and return out. That's it. Right. So let's see what we did. 16 is the goal. We created a cache. The cache is global. We don't have to pass it. If cache of I comma j not equal to 0, we return that value, else we fill it up. Okay, run. 10, new value 10. What the fuck? Okay, what did we do wrong?
I think we should not initialize 0 as default. Can we change it to -1?
Okay, and why?
I think because let's say if there is a cell value which is 0. Okay, can I see the input ones?
Yeah,
I
you're right.
thought,
You're right.
yeah, so it's not going forward. It's like it is not exploring other paths. It's just
Fair,
returning from 0.
fair. All right. Still, we're getting 10.
Okay, let's see. I- Wow, not sure. What did we do wrong? It looks right at first glance.
Fine. All right. When this happens, we go back to the drawing board. So let's see what we did there. So our basic instinct is to immediately try adding print statements, which I have been avoiding to do because that is an infinite loop. So pen and paper is always, at least personally for me, this is the best. Okay, so let's say we started our cache with, we filled it up with all -1. Sorry, where am I drawing that? Here, okay. -1, -1, -1, -1, -1, or whatever. Then we start with 0, 0. Need a minor of 0, 0. So where's the helper? Okay, 0, 0 coming in. I is 0, J is 0, cache of
Oh,
I.
I understood. I understood. I think,
What is it?
can we go back to the code?
No, wait, not time, not yet time. What is it?
Uh, when we are returning cache ij, do we need to add grid ij in when we- basically line number 28? Do we need to? No.
No, cache is separate, right? Cache is the value we are storing in there.
Right,
So
right.
okay, let's go back to, when I
Yeah,
get,
no, sorry.
so let's again go back to, no, Kelsey, go sit down. Okay. So that this is exactly when I go back to Fibonacci. So even I don't know what mistake we made, right? So instead, what I'm saying is, let's write Fibonacci again. Right, the 1, 2, 3, 4. This is the pure grid, our equivalent of grid. 0, 1, 2, 3, 4 index. While is 1, 1 plus 0 is 1, 1 plus 1 is 2, 2 plus 1 is 3. Okay, so now when we were building the corresponding cache for it, we started at 4 and we hard coded it with 0 and 1 values, right? And we started when we were, so this is the cache. And when we were asked the question fib of 4, we hard coded, we don't know what fib of 4 is. So we asked fib of 2 and fib of index 3 and index 2. And they also didn't know what their answers were. They asked this. So somebody knew the answers already. So I think we are not priming it anywhere. Should we prime it, right? Because remember, when we were creating cache, we already said cache of 0 equals 0 and cache of 1 is equal to 1. I'm thinking, remember when I was showing you this example on the right, did we not prime it? Like the last column was this thing, right? Because
Yeah,
when
yeah.
going back to the cache, it should stop somewhere. Right now, it is not stopping anywhere. It doesn't have anything in the cache value. So I don't know. That is my thought, just thinking this through. Any other comments?
Okay. No, can we try to add it in code, whatever you
Yeah, okay. This will be
are
fun.
thinking of?
So we definitely needs to prime it, right? So, but the only question is, what did we do wrong? Okay. So what is this cache of 0, 1, 2, 3? 0, 3 is 5. 1, 3 is, yeah, Deva. 1, 3 is 1, 3, 2, second row. Okay, we're going, this cache is filled up. Then we keep going. If when you come in the very first time, cache 0, 0, they don't know anything. They go to I comma +1, j comma +1. I mentioned finally it should hit some kind of cache. We return cache. Okay, and we are returning maximum of that, guys. I'm going outside. Let's see. Hope for the best. Ta-da. Oh my God. Different language, different language.
I do the same mistake many times.
It's even worse this time. All right, 7. All right.
Okay, this can be a good homework.
This
I
is a good
can,
homework. This is a good homework. At least we have come
yeah,
this far. I'm not even
yeah.
sending you this code because I want to write this up. I want you to write this top to bottom like I was writing it quickly. And once we like
Okay,
think this through, I'm pretty sure we will know what we are doing wrong.
okay.
Um,
Yes,
especially try to think it through the white paper. And this is my
okay.
plan, right? So even like right now we are in DP Goldmine. We are trying to add like
Mm,
a recursion plus memo plus iteration. Okay. Now I'll show you backtracking, which kind of we already did. If you remember, like root to leaf question, like print all the paths from root to leaf. We are going back up, like every time we did not find something, even like finding a node, right? So backtracking is nothing but just like when you don't know if this path is going to work or not, all you do is like here you have a tree, and let's say in this tree you are searching for a node 3, and we have nodes 4, 5, 6, 7, 8, and you start here, search, go this way, did not work, go back. So that is exactly your backtracking, right?
mhm,
So it's a very interesting concept. Like backtracking is, we are doing this naturally to ask the question if it exists. And it'll that's how it is showing up here in this problem as like, hey, this is find in the maze question, which you actually said, it's asking me this also, right? Tell me if a path exists out of this maze, right? So we'll show you the maze question, but in the lead code, that is what I feel was happening, that we have more condition, which is never visit a cell with 0 gold, right? It's you're not allowed to go there, and you can't even visit the same cell twice. So they are basically giving us restrictions on the path. So we don't even know
mhm.
the path. So we need to incorporate that also. That is my gut feeling.
Okay.